Hi, I'm Dave Robinson, and welcome to Makino's EC Live. Today we're going to talk about the EDAF version C. So these are the improvements on the version C machine. So we're going to show you a little presentation, and then we're going to do a walk around out at the machine in our showroom. So let's get started. So the first thing on the version C, we want to talk about the improvements. The work tank flow pattern. So this has changed from our previous models. What we've done is change the direction of the flow for more high efficient chip removal. So what that does is it takes the fluid from the back of the machine to the front of the machine instead of that tornadic movement that we had previously. Second, adaptive control. So what the machine does is analyze and self-adjust its machining behaviors to make the machine more efficient. Number three, the new HS rib cooling system. So we've had the HS rib system now for 5 or 6 years, and we've done some adjustments to that on the cooling side of it. So this is a continuous circulation of cooling oil. And then lastly, the filtration system. So we have a more high efficiency system for cleaning the oil and then creating that circulation. So right now I want to show you a little video of these same features. So now that we've seen the video, I want to talk about each one of the sections of the improvements of the machine. So the first one, the new work tank flow pattern. So you can see here, this is the rear of the machine. So the port outlet of the machine, where the oil comes into the machine, is in the back. And then the flow is towards the front where the overflow ports are. So the reason we do that is to take that debris out of the machine as quick as possible. We don't want it to get back into the machining area and be remachined. This creates a better surface finish and a better melting edge. So here you can see work tank left side view, so port outlet coming towards the front of the machine. So I just talked about improved edge quality and surface finish. So what that does with that better surface finish and the improved edge quality is that minimum melting edge. So we don't get that debris on the top of the edge that has to be removed by hand or polished off because of that improved flow. It takes that material off and we don't get that redeposited edge on the part itself. So this improves the fine edge quality as well, and then also enhances the surface finish. So the machine is equipped with smart logic control to streamline that flow at a smooth rate without mixing the debris in that tornadic motion. It's more of a laminar flow from the back to the front of the machine. So what that does is eliminates the pinholing and also gets a better, more consistent surface finish. Next improvement, new adaptive control function. So our adaptive control basically controls the machine during its machining. It monitors the spark, monitors the jump. So with the new adaptive control, it is called AiSF. So this is an adaptive spark function. What it does is the cycle time now is adjusted, the jump cycle, according to the stability of the machining process. So what that does is shorten the cycle time of the machining. How it does that is basically as the machine gets in trouble or that spark basically is ineffective, or the effective pulse weakens, it increases that jump frequency. Previously, most machines would add off time to stabilize that function, and what that did is increase the cycle time and also increase the wear. So now by just adjusting the jump, we don't get that cycle time increase. Also, one of the features that's a resultant of that is a uniform wear on the electrode itself. So you can see a photo here that we get a more consistent electrode wear. We don't get buildup on the corners of the electrode, or we don't get the abnormal wear. One of the results of that is no arcing during high-speed machining, so that adaptive control basically makes that very optimized. So it's automatic software adjustments that include jump settings and also that reduction of machining time. So again, here it shows the adaptive control side in the wear. So with no adaptive control, we get a small buildup on the corner, where with that AiSF, we don't get that buildup on the corner, so there's no damage or buildup to the electrode. Next feature is the new high-speed cooling system. So this is the high-speed cooling on the HS rib. HS rib is the 20 meter per minute jump in the z-axis direction at 1.5 G acceleration. So here's a little view of the cooling loop itself. So we have the machine oil-matic. So this is the dielectric chiller. So it goes from the dielectric chiller through the heat exchanger, from the heat exchanger to the spindle itself, and then also connected to the bed tank. And then the heat exchanger in addition, is connected to the z-axis. So we put cooling through the z-axis and the spindle through the motor block and core cool the ball screw at the same time to take any of the thermal growth or the thermal heat that's created in that 20 meter jump process. So we get a faster machining time with that thermal stability, that we don't get growth. It's a much more robust z-axis. Again, 20 meter per minute jump, 1.5 G acceleration, and generally about a 30% time savings with the HS rib system over standard jump. Standard jump is only 5 meters a minute, so 4 times as fast jump. The faster we can get back into the cut, the faster the machine's going to advance and remove material. So it also has stable thermal control, so that heat exchanger, again, for dissipation of heat and to preserve the accuracy or high accuracy of the machine. Lastly, the new filtration system. So we've created a new filtration system. So we go from the bed tank through our filtration, so the filters themselves, and then we introduce only clean oil into the work tank. Previously, the machines would only filter the oil that came from the bed tank, and it would fill the work tank with what oil was available from the bed casting. So now any oil that goes into the tank itself has been cleaned. That also is a good result on the surface finish side as well. Filter usage range has increased. Previously it was only from 0.1 to 0.2 MPa. Now we go to 0.3 MPa. What that does is gives us 10% more filter life. Also, the diameter is smaller and lighter. It's a smaller filter. So previously it was a 400 millimeter filter. Now we are down to a 210 millimeter diameter filter. It also uses thin paper technology. So it gives us more paper and more surface area to trap that debris in. So it's a much more efficient system on the filtering side. With that filtration system, we've taken those canisters, we've taken them from sitting vertically, and now, like you see in number 1, they sit horizontally. So with that, there's less parts to remove. It's a much more simple maintenance system to change the filters. So we have the canister itself, the paper filter that's inside, and just 2 parts to remove to get to that paper filter. So there's the lid and then the nut itself that holds the filter in. So, and with this canister system, 100% airtight system, so less chance for leaks. So the filtration system is really an efficient supply of clean oil. So really the biggest features are the direct transfer of clean oil from the filtration directly to the work tank, where previously there would be some particulate in the oil. 30% faster to obtain that clean oil, so much more high efficient system with that thin paper and more surface area. And then sustainable filter life, that we get 10% longer filter life on the filters, so really saving money at the same time as being efficient. So we're done with the presentation side of the EDAF improvements. So I'm going to go ahead and walk out to the machine now and do a live walk around of the machine. Okay, now that we're out at the machine, we're going to go ahead and go through each one of the features we had talked about in the presentation and do a live walk around of the machine. So the first one we want to do is tank fill, to show you where the tank flow comes from. So I'm going to go ahead and fill the tank. You can see that it comes from underneath. It flows from back to front. So once the tank gets filled, the float upper hits, then we can see that laminar flow from the back of the machine to the front into the overflow ports. That's what's going to carry that debris out quickly and get it out of the burn area, give us better surface finish, better melting edge. So now that the tank flow is stabilized, you can see the flow coming towards the overflow ports. So second feature we talked about was the AiSF, or the Adapti Spark function. So I'm going to go ahead and run a program, a rib, to show you that Adapti Spark function in action. Also, you'll see the 20-meter jump of the HS rib as well. So electrode rotates 90 degrees, comes down to our start point, and then we start to burn. So at this point, you can see the AiSF on the screen active. So that's the Adapti Spark function. That's our adaptive control. So anytime the electrode gets into trouble, or it has problems, it stumbles, that there's debris in the way, it's going to then continue to jump instead of adding off time like it did previously in our P-pulse adaptive control. So at the same time, you see the 20-meter jump again. So a 20-meter jump, 1.5 G acceleration. So that rapid jumping motion is what's taking the debris out of the cut. And you can also see at the same time that laminar flow of the debris heading towards the front of the machine to go out of those exit ports and get out of the way. So the next feature we want to talk about is the new improved filtration. So filtration's in the same spot, but filtration has definitely changed. So again, smaller filter, 210 millimeter diameter filter, opposed to the previous 400 millimeter filter. The thinner paper, so we have more surface area. So you can see here, nice catch tray to drain the oil. So the system sets now horizontally instead of vertically. So much more efficient system, about 30% faster for turnover of oil. So nice filter replacement procedure on the side of the machine as well. So very simple, easy to change filter. So the last feature I wanted to show you today is the heat exchanger. So this is the heat exchanger that cools the Z-axis. So this is what cools the Z-axis stabilizer. We pump the Makino spindle lube, same thing that's in our mills, up through the Z-axis, that core cool ball screw, also the motor blocks as well. So that takes any of the thermal growth out of the spindle itself and the Z-axis at the same time. So that's how we hold that precision and depth control while still jumping in that 20 meters per minute at 1.5 G acceleration. All that concludes my presentation for today on the EDAF version C, the upgraded features of the EDAF. I'm going to go ahead and head back into the EC Center to take questions. Down in the lower right of your screen, there's a chat feature. If you'd like to ask any questions about any of the Sinker content or anything we covered today, please feel free. So ask any questions. Thank you.
All right, thanks, Dave. My name is Brian Coward. I'm the product manager for EDM here at Makino, and Dave and I are now available for any questions that you may have concerning the EDAF 3 and 2 improvements that we made to that series machine. as well as any general EDM questions that you may have. So you can see there is a chat window there that you could type in a chat. There's also a Q&A section where you could type in a question if you have any questions for us. We're available to take any questions that you might have. So I do have a question myself for Dave. So Dave, you're talking about pinholing. So I just wondered if you could kind of explain what you meant by pinholing and what that is and how the flow improvements on the machine improve that.
Yeah, so when we refer to pinholing, these are microscopic pits that are in your workpiece material. So that pinhole is created by the graphite particle or the steel particle or whatever your workpiece is, and it's reburned back into the part itself. So they are very microscopic. I mean, sometimes under a micron in size. So those microscopic pinholes, problem with that is sometimes they don't polish out if you polish, especially in your higher surface finish applications when we get under a 5R max surface finish. So really, really good surface finish. And the biggest thing is with that laminar flow and pulling that debris out, it's not getting reburned back into that material. And that's really what eliminates that pinholing. So they're very microscopic. A lot of times you're not going to see that pinholing until you put a part under a microscope or you do the polish, and then they really show up. Almost when it's polished, looks like you poke the surface with a pin. And that's why they refer to it as pinholing.
Okay, very good. We did have another question that we received prior to this presentation, and it had to do with the AiSF, the adaptive control improvements. So that changes both jump and current, correct?
It changes. So its first line of defense is the jump. So it increases that jump frequency as that part loads up with debris. Basically, we're not getting the debris out fast enough for the electrode to advance quickly. So the first line of defense is to increase that jump frequency. Second, then, if the jump doesn't take care of it, we still see a problem where the machine, the adaptive control, sees the problem. It then goes to its second line of defense, which would be to add off time to the cut. And then the jump frequency as well will adjust again, or adjust what we call cycle jump or cleaning jump. So there's many types of adaptive control going on at the same time. And the machine's adaptive control really is trying to get back to 100% efficiency. So the settings that we set in the project programming is what the machine will try to run off of, and the adaptive control then tries to work with those settings and to make those adjustments to keep it at 100%.
Okay, good. Looks like we have another question here from Cameron. Is a Z-axis or HS rib Z-axis chiller separate from the working fluid chiller?
Yeah, good. Actually, a good question. So the Z-axis chiller, basically what we refer to as heat exchanger or stabilizer, actually runs Makino spindle lube. So same thing that would be in a mill. So that is separate from your EDM fluid or the dielectric fluid. So the dielectric fluid is pumped through like the motor blocks, along the ram on the y-axis in the EDAF product. And that is the dielectric oil, where the HS rib Z-axis stabilizer or heat exchanger has that stabilizer fluid in it. So it is a separate sealed system, goes to a heat exchanger, so it's completely separate. So with that too, the ball screw itself is core cooled, and that's what's going through that chiller. So it maintains the same ambient temperature as the dielectric chiller, but they work separately. So one removes heat from the Z-axis, and the other then removes it from the rest of the casting, and then obviously from the working area.
Okay, very good. Tom has a question about advantages of the ball screw Z versus a linear drive Z.
Oh, very good question, actually. So one of the things I really like to talk about. So ball screw, like we had said with the HS, 20 meter per minute jump at 1.5 G acceleration. So the bigger point of that acceleration rate is that 1.5 G acceleration. So if you think of it as like the 0 to 60 time in your car, it's how fast we get up to that top speed. So that 20 meters a minute. The 1.5 G acceleration is really the key to get us to that jump speed faster. In sinker, a lot of times that jump distance is very, very small. So the faster we can get to that acceleration rate, that's really what is the big advantage of pulling that out. So linear motor, as you know, very, very fast. So fast movement. It's a lot of times though, it's the acceleration rate isn't as fast, and you do get a little bit of lag on the top end and bottom end when it basically does that direction reverse. So there's a feature called hysteresis. That is that lag when a linear motor changes direction. So just like it would do in a wire machine when it changes directions, when the X and Y change, you get that slight. I mean, it's ever so slight in the linear motor, but it is there. And the other part is the heat that's generated by a linear motor, much more heat to pull out. So just like our HS rib machines, we use an independent chiller. So that Z-axis stabilizer, just like in the question before, in the linear motor, much more heat generation. So that heat has to be removed from that Z-axis. Otherwise, we're going to get thermal distortion and growth. And that's where your depth control issues come in when we can't get rid of that thermal. So generally, we can hold a micron of accuracy as far as that jump goes in our depth control because of the heat being pulled out quickly.
Yeah. So it's just easier to manage that heat in the Z-axis as opposed to with a linear motor. Because I know that in the past, Makino has made machines with what we called a rib head back in the day, and that used a linear motor, which would generate a lot of heat, and it was a little more difficult to remove that heat versus a ball screw with the HS rib.
Correct. Yeah, it actually jumped at 40 meters a minute, but it didn't have the G acceleration rate. So the resultant wasn't actually as fast. And the other part of that, the depth control with that linear motor was not as good. So we could rough with it, and then when it's time to do the finishing, we'd actually lock up the linear motor, and then the Z-axis would take over and do the jump. So with the HSF, we went away from that linear motor design.
Okay. And then to follow up on that question, we'll jump over to autos because it's in the same, talking about the same subject. He asked, is the 1.5 G acceleration, what is the max weight of electrode that you could really maintain that?
No, excellent question. So with the control, what it looks at is the frontal contact area when it's doing the programming. Anything that's over 2 inches of square area, then it starts to cut back that jump speed. So with that, think about basically stepping in mud with your shoe. That surface contact area, the surface tension that it creates, you create a suction or basically hydraulic force. So the larger that flat area is on electrode, or the larger surface area, the more chance for that hydraulic effect. So the machine will actually slow down that 1.5 G acceleration and the speed as well to match what that frontal contact area is. And that's based off the programming as well. So to protect that electrode. So if you had a 4-inch electrode, we're definitely not going to jump at 20 meters a minute. We may drop down to 10 meters a minute. So the machine does that to protect the electrode.
Okay. So that makes sense. So it's based on the frontal area, which in turn really equates, will be the size of the electrode.
Correct.
And the machine knows that automatically.
Yep. And it will actually lock out the HS function from being programmed once you put that electrode size in to prevent damage to that electrode. Or we've even seen parts when you jump at 20 meters a minute with a large electrode, it can physically pick a part off a magnet and move it.
Yep, suck it up. Yep. Okay. Doug has a question. In aerospace applications require low remelt and very little or no white layer. Can this adaptive control, that the new adaptive controls and everything, what is that going to do to those specific issues?
Another good question. Aerospace, recast, has, and microcracking are the three really big items that we look at. So definitely to the adaptive control side helps that, by controlling the spark better. One of the features that all of the machines now have what we call our ES200A generator. So it's a digitally controlled generator, where our previous versions a few years ago were just an analog version. So we can control that spark better. And again, more finite spark, so finer finishes as well, and less power to do basically the same type of burning that we did in the past. Recast itself, it cannot be completely eliminated. It doesn't matter if it's wire or sinker. We can't say that we can remove it. We can say virtually eliminate. So it's really more based off of surface finish. So the better the finish we go to, the less remelt and less white layer, what we call has. And then, of course, micro cracking is decreased or completely eliminated at that point. So the adaptive control definitely helps in that case with that digital generator to eliminate a lot of that, depending on what finish you go to.
Okay. All right, very good. Cameron has another follow-up question here about the HS rib and it looks like the adaptive control. Is there a way to employ the jump-based adaptive control on an older EDAF or EDNC?
So the older EDAFs and EDNCs still have an adaptive control system. It's called P-Pulse. So P-Pulse, its first line of defense was to add off time. So you'll see an off time multiplier on your MGH6 or the early ES100 Hyper-I generator machines. So another way to control that, though, is the cycle or cleaning jump. So we can control that cleaning jump a couple different ways. In the programming side, we can do a variable cleaning jump. So that variable cleaning jump on the way down, in the beginning, of course, you're shallow, not as much need for that cycle or cleaning jump. So what it does is it looks at, as it gets deeper, it increases the frequency of that cleaning jump on its own. So that is part of the programming and adaptive control. We have both a fixed and a variable cleaning jump. So if you do really deep work, especially ribs, the variable cleaning jump is programmed in the G132 line to take care of that issue. So if you have any questions on that, you definitely can call into one of our technical support specialists that do the EDM side in applications, and they can explain that programming.
Okay, very good. All right. Well, let's see. I don't think we have any more questions here. Looks like that's it. So I want to thank everyone for taking some time out of their day today and joining us for this presentation on the improvements on the EDAF series machines here at Makino. If you have any questions on the EDAF or anything else EDM related, contact myself or Dave Robinson, and we'll be more than happy to answer any questions that you have. So thank you, everyone, and have a great day.